Imagine standing on a windswept plain, the sun warming your back as you scan the horizon. Below your feet, hidden beneath layers of dust and rock, lies a secret. It is a story millions of years old, a tale of creatures grander and stranger than anything we know today. This is the world of paleontology. It is an adventure not across oceans or continents, but through the immense, silent corridors of deep time. Each discovery, whether a colossal bone or a delicate leaf imprint, is a clue, a key that unlocks a chapter of Earth's epic history. The thrill of this science is one of pure discovery. It is the feeling of being the very first person in millions of years to lay eyes on the remains of an ancient life form. One moment you are brushing away sediment from a seemingly ordinary rock, the next, the distinct curve of a rib, the serrated edge of a tooth emerges into the light. In that instant, a connection is forged across an unimaginable gulf of time. You are no longer just an observer of the present. You have become a time traveler, touching a tangible piece of a forgotten ecosystem, and breathing life back into the story of a creature that once roamed this very planet. This journey into the past is filled with wonder and immense patience. It requires a keen eye and a deep curiosity about the natural world. Paleontologists are detectives of the Earth, piecing together clues to solve the greatest mysteries of life. They seek to understand not just what these animals looked like, but how they lived, what they ate, and why they disappeared. At its heart, paleontology is the science of ancient life. The name itself comes from Greek words, paleos meaning old, ontos meaning being, logos meaning study. It is, quite simply, the study of old beings. This field of science is our window into prehistoric worlds. It allows us to explore ecosystems that rose and fell long before the first humans ever walked the earth. Paleontologists are the historians of life itself. They do not read ancient texts or study human-made artifacts. Their library is the rock of the planet. Their words are the fossils locked within, each one a testament to life's incredible journey. The scope of paleontology is truly vast, stretching back billions of years to the very first signs of simple, single-celled organisms. It is not just about dinosaurs, though they are certainly its most famous subjects. This science encompasses all forms of ancient life. It includes the study of colossal mammoths, the strange sea creatures, the first insects, and the enormous ferns. It is the story of every plant and animal that has ever lived, a chronicle of evolution, extinction, and survival on a planetary scale. Paleontology is the grand narrative of our planet, a story of resilience and transformation that reminds us of life's fragility and its incredible enduring power to persist through the ages. A fossil is the preserved remains or traces of a living thing from a past geological age. It is a rare and precious miracle of nature. For an organism to become a fossil, a very specific set of circumstances must occur. Most living things, when they die, simply decompose and disappear. Their organic matter is recycled back into the ecosystem. But occasionally, just occasionally, the conditions are perfect. The remains must be buried quickly, usually by sediment, mud, sand, volcanic ash. This rapid burial protects the organism from scavengers, decay, and the elements. Step 1. The dinosaur dies near water. Step 2. Its body is quickly buried by sediment. Step 3. Over millions of years, minerals replace the bone. Step 4. Erosion eventually exposes the fossil. Once buried, the process of fossilization, or permineralization, can begin. Over thousands and millions of years, more layers of sediment pile on top and pressure increases. Water rich in minerals seeps down into the tiny pores of the buried remains, silica, calcite. Over immense spans of time, the original organic material decays and is completely replaced by these hard, durable minerals. The shape is preserved, but the substance has become rock. There are several different types of fossils, each telling a unique part of the story. Sometimes insects get trapped in tree resin that hardens into amber. Amber can preserve three-dimensional detail perfectly. Each type of fossil is a different kind of message from the past, a unique whisper from a long-lost world. The search for fossils is a true adventure that often begins not with a shovel, but with a map. Paleontologists are expert geologists who know how to read the story of the land. They look for sedimentary rock formations of the correct age, the kind of rock formed from ancient mud, sand, silt that is perfect for preserving fossils. They study geological maps, satellite imagery, to identify promising locations, often in remote and rugged places like deserts, badlands, and mountain ranges. These areas, where erosion has stripped away younger layers of rock, are ideal hunting grounds as they expose the ancient layers where prehistoric treasures may lie sleeping. Once a promising site has been identified, the real fieldwork begins. This is a slow, methodical process that requires immense patience and a sharp eye. Paleontologists will walk for miles, scanning the ground for any sign of fossilized bone or shell fragments that may have weathered out of the rock. The tools of the trade are often surprisingly simple: a rock hammer, brushes of various sizes, a hand lens. Every discovery, even the smallest fragment, is carefully documented, its location marked with GPS so that a complete picture of the site can be built. When a significant fossil is found, particularly a large one like a dinosaur skeleton, the process of excavation begins. This is delicate and painstaking work. The goal is to remove the fossil from the ground without causing any damage. As the fossil is uncovered, it is often coated with a special glue-like consolidant to strengthen it, as ancient bones can be incredibly fragile. It is a surgical operation on the landscape where every move must be precise and thoughtful to protect the irreplaceable specimen. They then cover the exposed fossil and the pedestal with layers of plaster-soaked burlap strips, creating a hard protective shell known as a field jacket. This jacket ensures that the fragile fossil remains safe during transport to the lab, where the even more meticulous work of cleaning, preparing, and studying the specimen can finally begin. Once a fossil is brought back to the lab, one of the most important questions a paleontologist must answer is, how old is it? Determining a fossil's age is crucial for placing it within the grand timeline of life's history. There are two main methods for doing this: relative dating and absolute dating. Relative dating does not provide an exact age in years, but instead determines whether a fossil is older or younger than other fossils or rock layers. It is based on a simple but powerful principle known as the law of superposition. This law states that in a sequence of undisturbed sedimentary rocks, the oldest layers are at the bottom, and the youngest are at the top. Imagine a stack of newspapers. The one you put on the pile yesterday is on the bottom, and the one you added today is on top. Rock layers work in much the same way. By observing where a fossil is found within these layers, paleontologists can establish its age relative to other fossils found in the same sequence. For example, if a fossil of an early mammal is found in a layer above a dinosaur fossil, we know that the mammal lived after the dinosaur. Scientists also use index fossils, fossils of organisms that lived for a very short specific period of time but were geographically widespread. When an index fossil is found, it helps to correlate the age of rock layers in different parts of the world. For a more precise age, however, scientists turn to absolute dating. This method provides a numerical age in years, and the most common form is radiometric dating. This technique works like a natural microscopic clock that is built into the rocks themselves. Many rocks contain tiny amounts of radioactive elements such as uranium or potassium. Over time, these unstable elements decay at a predictable, constant rate into more stable elements. For instance, uranium-238 decays into lead-206. By carefully measuring the ratio of the original radioactive element, the parent, to the stable decay product, the daughter, in a rock sample, scientists can calculate how long it has been since the rock first formed. It is important to note that fossils themselves are rarely dated directly using radiometric methods. The process of fossilization replaces the original organic material, which would have contained elements like carbon-14 with other minerals. Instead, paleontologists date the layers of volcanic ash found above and below the fossil. By determining the age of these ash layers, scientists can constrain the age of the fossil sandwiched between them. This combination of relative and absolute dating allows paleontologists to build an incredibly detailed and accurate timeline of Earth's history. Perhaps no discoveries in paleontology have captured the human imagination more than those of the dinosaurs. For over 150 million years, these magnificent creatures were the dominant terrestrial vertebrates on our planet. The first scientific discoveries of dinosaurs in the 19th century shattered our understanding of Earth's history, revealing a world ruled by reptiles of astonishing size and diversity. Finds like the colossal skeletons of Argentinosaurus in South America, a creature so immense it would have dwarfed any land animal alive today, continue to inspire awe. These discoveries paint a picture of a vibrant and dynamic Mesozoic era, a time of giants that roamed the continents. Equally compelling are the fossils that tell the story of our own origins. The discovery of early human ancestors, or hominins, has provided profound insights into our evolutionary journey. In the 1970s, the discovery of Lucy, a 3.2-million-year-old skeleton of Australopithecus afarensis in Ethiopia, was a landmark moment. Her skeleton proved that our ancestors walked upright on two legs long before the evolution of large brains. Each new hominin fossil found, from the ancient footprints preserved in volcanic ash at Laetoli to the more recent discoveries of species like Homo naledi in South Africa, adds another crucial piece to the complex puzzle of human evolution. Beyond these famous examples, paleontology has unearthed entire lost ecosystems. The Burgess Shale in Canada is a treasure trove of fossils from the Cambrian explosion, a period around 500 million years ago when life suddenly diversified into a bizarre array of forms. Here we find creatures that look like nothing alive today, with strange body plans that represent evolutionary experiments, many of which did not survive. These fossils show us that the history of life is not a simple, linear progression, but a vast, branching tree with many dead ends. Another revolutionary discovery was that of feathered dinosaurs in China, such as Sinosauropteryx. These fossils provided the first undeniable evidence that modern birds are the direct descendants of dinosaurs. The delicate impressions of feathers preserved in the fine-grained stone offered a stunning confirmation of a long-held scientific theory. It completely changed our perception of dinosaurs, transforming them from slow, scaly reptiles into active, dynamic animals, some of which were covered in plumage. These finds beautifully illustrate how paleontology is a constantly evolving science, with each new discovery having the potential to rewrite what we thought we knew about the deep past. The stories written in stone are not just tales of a lost world, they are vital lessons for our own, reminding us of our place in the long, magnificent, and ongoing story of life.